signal communication or signal traveling through RC interconnect. So if in case of graphene there are two possibilities. If the length of the graphene interconnect is longer than mean free path, then the signal will travel through this graphene interconnect like an RC interconnect. If the length of the graphene interconnect is shorter than mean free path, the signal will travel at ballistic speed, almost at the speed of light. Because for very short length, it will have negligible or no resistance. So, for any interconnect medium, having longer mean free path is beneficial because electron then can travel through that distance in ballistic speed.
We want small interconnect and longer mean free.
Mean free path, yes. So if the length of the interconnect is shorter compared to mean free path, then yeah, definitely you can get ballistic speed. Of course, we will lose something in the contact resistance. So what is a ballistic interconnect? If we want to define, a ballistic interconnect is the one that has a length less than mean free path, because then in between it will. So the question is, in a practical design, if we want to implement this practical design, interconnect design using graphene, in ideal truly ballistic interconnect, the resistance will be 0 from point A to point B, but practically there will be some resistance because there will be no ideal ballistic interconnect. So there will be some resistance even without the contact resistance, because it depends on number of conduction channels and another parameter called quantum resistance inside graphene. So, but in general, within this mean free path, the effective resistance of graphene interconnect will not be 0, but it will be a finite number which is significantly lower than resistance of any identical size metallic interconnect. So, going backward. Okay. So, so any graphene, practical graphene, 2D graphene will have some finite quantum resistance, and this is a well-known formula that actually can be used to estimate quantum resistance of a graphene nanoribbon. So first, let us look at this structure. So what is the difference between this structure from carbon nanotube? Tubes are tubes. It's a concentric tubular structure of graphene sheet. But if we unroll that graphene sheet and cut it in narrow ribbon shape, then we call it graphene nanoribbon. So this graphene nanoribbon, each one of them will have some quantum resistance, finite quantum resistance. So in a practical graphene-based interconnect, even if we can implement it with negligible or small contact resistance, it will have a finite resistance, so it will not be truly ballistic. Also, in any practical graphene-based interconnect, we have to put multiple graphene nanoribbon in parallel. Like in any electrical wire, you see bundle of small wire. In any carbon nanotube interconnect we discussed, it will be a bundle of tubes. Similarly, one graphene sheet, including its contact resistance, will not be enough to carry the required signal. So you have to put multiple parallel graphene sheet between each pair of contact. So from here to here, there will be multiple current path like the bundle of wire. So this is called multi-layer graphene nanoribbon. and all those will be contacted from end to end. In this contact interface and in this contact interface there will be contact resistance. Contact resistance, and that should be added to this quantum resistance, so to calculate the actual resistance of practical graphene nanoribbon based interconnect. So another important factor in case of practical issue, in case of implementing graphene nanoribbon, is this graphene nanoribbon we are talking about sub-nanometer scale graphene sheet, less than nanometer thickness. It cannot be just hanging there between two pair of contacts. It has to be grown on a substrate, one layer on top of each other. So the substrate material on which the graphene nanoribbon will be grown or placed, and the contacts will be from the side by side, right? That substrate will have a tremendous impact on the performance and behavior of graphene-based interconnect. So in conventional IC process, the most important and common substrate is the silicon dioxide, silicon or silicon dioxide. So these are the different parameters based on experiments done by mean free path for different graphene samples placed on different types of substrate. So this is kind of a summary of this experimental observation based on graphene nanoribbon sample placed on different substrates. So it tells us that we can come up with, even if ideally we can come up with a pure aligned graphene nanoribbon, the contact will introduce first non-idealities, and then the substrate will add additional impact. So what we ideally expect from a 2D graphene nanoribbon, actual performance will be significantly different because of the impact of contact resistance and substrate. Then also geometry, the structural property of graphene nanoribbon will also have some impact on its performance as interconnect. The wider and narrower width compared to the length are those, when you cut the ribbon like this, there will be some dangling bond, right? If you basically cut a sheet of cloth, at the end there will be some loose threads, right? Similarly, graphene, 2D graphene is like a honeycomb shaped atoms. So when you cut it, at the edge there will be lots of like half honeycomb, right? Dangling bond, dangling atom on the edge. So those geometric properties, width versus length, and also the edge properties will have impact on the graphene nanoribbon performance, its conductance, its resistance. So these are different observation based on changing width, how changing width changes the mean free path, how changes with resistance per unit length, and also with the change the sheet resistance per unit area sheet resistance. So all those things, different research group, they basically try to calculate using some rudimentary experimentation and some theoretical analysis. Now, let's talk about multi-layer graphene nanoribbon. As I mentioned, one single graphene sheet contacted placed between two contacts will not be good enough. There has to be multiple layers of graphene nanoribbon placed in parallel. But the problem, and this entire arrangement will be placed on a substrate. But the problem is when you place, let's say, 1, 2, 3, 4, 5 layers of graphene nanoribbon on top of each other on the substrate, how do you provide the contact? In traditional IC design, all the metal depositions are from the top surface. There is nothing from the side. It's layer by layer. So if we first deposit the substrate, on top of it, if we deposit the multilayer graphene nanoribbon, we have to deposit the contact here. So the contact material will be only touching the top layer. So this layer will be dependent on sending signal this way, vertically. But ideally, what we expect, if I can touch each nanoribbon edge from this side and this side, contacts are sidewise, then everybody can send the signal to the outside circuit equally with equal resistance, right? But practically, so this is ideally what we expect from a multilayer graphene nanoribbon. But practically, contact materials are deposited from the top. All the materials are deposited from chemical vapor deposition, one layer at a time. You deposit, you etch where you don't need, you keep where you need, right? So that's how it happens. So now, then the problem is, from the top layer to the bottom layer, each one will experience different resistance as signal has to cross one from air layer to another layer. So there will be interlayer resistance. And if they have different strength, it may also rise to interlayer capacitive coupling and other interferences. So that is one of the biggest difficulty is providing contacts in this type of bundles of carbon nanotube or multiple layers of graphene nanoribbon, which is required to implement any practical interconnect. So, but we concluded that we need multiple layer of graphene nanoribbon instead of single layer graphene nanoribbon for interconnect application, because when you put multiple layers on top of each other, parallel combination of multiple layer will bring down the total effective resistance. So, once we concluded that we need multiple layer of graphene nanoribbon as an interconnect application, you as the designer, what are the critical factors you have to consider? Now the question is, well, multiple layers, but how many? 5, 6, 7, 8, 9, 10, how many parallel layers on top of each other? That is one. And then contact method. Is it going to be vertical contact or side contact? If it is vertical contact, only the top layer is properly contacted. If you put 11 or 12 layers, the bottom layers probably will not contribute anything to the conduction because all the vertical resistance will come into picture, right? So we have to, the two of the very important design factors for multi-layer graphene nanoribbon based interconnects are the optimum number of layers and the contact method. So again, some people did some simulation about the number of layer with the width. So, and this is basically for different length. They change the width and number of layer. And at one point, initially, with the increase of width, the number of layer required decreases and then it kind of saturates. So that means we have to find an optimum number for a certain width, for certain length, and what would be the effective number of layers you need. So the contact, ideally side contact, which we need. Practically what we have is the top contact, right? So then this is purely theoretical analysis my student did using NanoHub 2. He just created these two model in NanoHub, side contact and top
So
contact.
NanoHub is a simulation software?
Eh?
NanoHub is a simulation software?
NanoHub is a platform hosted by Purdue University West Lafayette, funded by National Science Foundation. So for all those exotic simulations, there is no standard simulation tools. So they have lots of simulation models, simulation methods developed over the years, collected from all over United States, those who are funded by NSF, and they made it freely accessible. So you have to spend some time on NanoHub to know exactly what are the different simulation capabilities they have and how to write those models. So they don't give you the source code, but if you upload your data and you can simulate it, you will see the result. So NanoHub is a website, is an online digital platform hosted by Purdue University, funded by National Science Foundation, with the condition that it has to be made open for all.
Has there been any research, like has anyone been able to even deposit side contacts at all?
There have been effort.
I was wondering on something, like, is it combined the computational chemistry within NanoHub research, this type of things? Because
I did not spend that much time. I always ask my student. So NanoHub has from fundamental material level simulation to advanced application based simulation capability.
because a material, how charge, sometimes charge density can measure actually how the charge can transfer from the plate of this type of thing. So there is a few things of chemistry
Yeah.
also related with that. So I was wondering.
Then you to find that answer you have to go to NanoHub and explore. Yeah, because I stopped using CAD tools 24 years ago or 20 years ago. Ever since I graduated, so I never touched any
NanoHub,
CAD tool.
does it have any user interface, graphical user interface?
Yes.
Or is it like
Yes. I as far as I remember, I logged in once or twice. It has not like very smart, but it has some graphical interface. So best way to find that, spend some time on NanoHub. Yeah. So in this simulation, what my student did, he actually used the top contact and side contact to see the delay for a certain combination of multi-layer ribbon. As you can see, with the increasing number of layers, when you provide side contact, every layer is contributing, delay is decreasing. With the top contact, delay is, with the increased number of layers, only the top one is good, then all the additional interference and this interlayer resistance is actually increasing the delay. So this is a very simple observation, which kind of agrees with our normal understanding. So this is another simulation. He continued energy delay product. The how much energy and delay. So basically, in some of the IC design, energy delay product is more important because it also gives you delay versus power consumption compromise. And as you can see, with top contact is increasing, but with the side contact it is increasing, but not as rapidly as the side contact, the top contact. So this is another kind of simulation. So in this work, what my student and I try to understand, basically through other research and our own simulation, we try to understand what are the design factors you as the designer, you have to deal with if you want to use multi-layer graphene nanoribbon as an interconnect application. So that ends, this is a relatively short part, and that leads us to the third part of this lecture, a similar topic. So in earlier we have shown you first part carbon nanotube based interconnect, second part is graphene nanoribbon based interconnect. And now let's see some examples, what people are exploring to use graphene and carbon nanotube for transistor, because when we are talking about any logic circuits, we need interconnect, we need transistor. By connecting those transistors using interconnect in different ways, we get AND gate, OR gate, NOR gate, adder, subtractor, right, multiplier, all the components for your microsystem. So when you are talking about graphene or carbon nanotube based or any nanomaterial based micro or nanoelectronic system, fundamentally what you need a bunch of transistors, you need a bunch of interconnecting wire. So you have to explore whether those nanomaterial is suitable for both interconnect and transistor application. So we have talked about interconnect application of graphene and carbon nanotube. Now let's talk about field effect transistor. So this is kind of a graphene layer, a bilayer graphene. So now what people are trying to do, one possibility is on conventional silicon substrate, we use SOI device. So silicon substrate, we have silicon dioxide in conventional SOI device. On top of that, we have a silicon channel connected between source and the drain. And on the top, we have insulated gate. In conventional, that gate is insulated by silicon dioxide. So in a regular SOI silicon device, this channel made of silicon is covered by silicon dioxide as an insulator from bottom and the top, and the gate is connected on the top, and the channel is connected with source and drain on the side. So if we want to exactly implement the graphene based transistor in conventional SOI structure, what we would do? Instead of silicon, we used a graphene channel or carbon nanotube channel. That becomes one possible way of implementing graphene based FET. And as I said, in a conducting channel, we want to put multiple graphene layer, so it will be multi-layer based graphene nano FET. So that is one way of implementing it. Another way, well, we can basically want to explore some other material, because we want to, people are now exploring other insulator for the gate area for better performance of the transistor. Conventionally, you have silicon dioxide below and silicon on top. So people are exploring aluminum oxide and hafnium dioxide as the two possible alternatives for silicon in the channel area, because hafnium will provide higher capacitive potential for the same width, same voltage, so it will make the transistor stronger. So because it has a higher electrical permittivity. So in this design, it's just a line diagram. We will have silicon dioxide at the bottom, separating the silicon body. Then we have bilayer graphene as the channel. On top of it, we will have hafnium dioxide as insulator. Of course, in between, we have to have some neutral material to prevent any chemical reaction between hafnium and graphene. And then gate will be top. But this is also same structure. The only difference is, instead of silicon dioxide separating the gate and the channel, here we are basically talking about another insulator. And as I said, hafnium oxide is one potential. In Intel Material Science Group, one of the things they do, like Michelle Packard here in our physics program, her research is all about exploring different insulation material for IC application, and she has been funded by Intel. So this is one way of implementing graphene nanoribbon based field effect transistor. So here you have the top gate, that yellow part, the conventional gate, and this lower silicon body, that also can be used in another gate. It's called back gate. So you can basically strengthen the channel by applying electric field, one from the top, one from the bottom. It's called dual gate device, top gate and back gate device. So this is another way. Now the question is, one of the problem, this is ideally what we want, but putting hafnium or any other insulation directly on the graphene is very challenging because there is a tendency of them reacting with graphene, and this graphene sheet is very thin. So we have to put another inorganic or organic material, polymer, which is neutral, will not react to either of them. But if you put this additional material layer, then the gate is going further away from the channel. The goal of having an additional, an alternative insulator so that I can make it thinner. Silicon dioxide has reached its vertical dimension limit in terms of thickness. So we can use some thinner or a stronger insulator with higher electrical permittivity. So, but here by adding this layer, we are increasing the distance, we are making the transistor weaker. So another alternative is, let's not use any gate on top. So some people thought about, well, can I have a back gate transistor on top of the dielectric silicon, this graphene layer will be placed, single layer or multi-layer, but the gate will be from the back. The electrical field will be applied from the back.
So, can you please go back to the
Yes.
slide? So
Okay.
there is you are using hafnium oxide, right?
Yeah.
Hafnium oxide as a which
In-
material?
Insulator.
Insulator. Okay.
So people, but in general, if you are interested, silicon dioxide has become the standard insulator for any IC application. But for higher gate strength, people are exploring, for exotic next generation devices, people are exploring at least 2 or 3 alternative insulators for IC application. And one of the popular in next generation silicon insulator is, alternative to silicon is hafnium dioxide.
Okay.
And another one is aluminum oxide, I think. They are exploring that as well.
But like, what is the purpose of adding insulation layer on graphene top of it?
Well, for any transistor, any field effect transistor, your conducting channel has to be insulated from the gate. Why? Because that is the field effect transistor's basic physics. The gate applies an electrical field onto the channel. Gate does not sense any current to the channel. So gate is insulated from the channel. That's how the field effect transistor action we get. We apply an electrical field from an insulated gate on top of the channel. So the channel has to be electrically insulated from the gate which is applying the electrical field. So applying a gate voltage, we turn on the channel. When we remove the gate voltage, we turn off the channel or the transistor. Yeah. So that is the basic requirement for it to be a field effect transistor. So backgate has a problem or a strength because typically this is insulation and then silicon body, so or the backgate, so it's much thicker. So the voltage we're applying from the backgate is far away from the channel. That's why in conventional MOSFET, gate sits on top of the channel so that we can apply the voltage at a very short distance from close distance. So that is one possibility people are exploring to avoid some material processing problem, putting gate and insulator on top of the graphene sheet because it will destroy the graphene's physical and electrical property. And the other option is like conventional top gate graphene FET. So graphene, find a suitable oxide and then put the gate layer. So that will be much more stronger transistor, but then you have to find out suitable oxide, silicon oxide, the insulator oxide, to be placed on the graphene FET. So This is another to improve graphene FET performance. It's called dual gate. So as you can see here, a graphene sheet placed on the silicon dioxide as the channel, and then we put source contact and drain contact. We have the top gate in between the channel, which is insulated by aluminum oxide. I'm showing it intentionally to just show you that there is another potential alternative for silicon dioxide people are doing research on as an insulator. And then you have a heavily doped P-type silicon as a back gate. So you have a top gate, you have a back gate. Now, same structure. All the previous structure we have talked about so far, these are all we are seeing that the channel will be made of graphene nanoribbon. What if we put the channel as carbon nanotube? So we can get same transistor structure, then it becomes a CNT FET based field effect transistor. So the channel will be made of silicon dioxide with the back gate, top gate, dual gate, everything we can implement using, theoretically we can implement using carbon nanotube. So this is back gate. So there should not be one tube, there has to be multiple tube in the channel so that you have more than one parallel path. So this is another way to do it, back gate. This is the top gate version. People have explored all the well, but all these research are purely theoretical. This is dual gate CNT FET. People try to implement. This is nano rod FET. Instead of like nano wire based device, it's like a rod of carbon nanotube or graphene. So you apply the gate here, you will apply source and the drain here.
So the difference between nano rod and nano wire is the radius?
No. In a nano wire based or nano rod based device, gate is applied all around.
Yeah.
It's a wire, it's
Okay,
a tube.
I got it.
Yeah. And in case of flat surface, gate only on the top or the back. Yeah. So the wire device and the regular device, that is the difference. It's gate all around. Yeah. So this is not truly gate all around, but it at least covers most of its periphery. That's basically increases the electrical field strength, and it actually also increases the transistor strength. So these are some of the different ideas, design ideas people are exploring, but for all the field effect transistor potential design I have explored, these are purely theoretical research. Somebody using TCAD or any simulation tools, they created this model, computational model, and changed the parameter, material parameter, physical parameter to basically this is the idea. I'm just showing you all the different explore. So biggest problem here in any of this design, number one is designing and implementing the right type of graphene nanoribbon or carbon nanotube that will maintain structural, physical, material integrity. It will have desired physical, electrical, material property and stability. That is number one problem. Number two is providing contacts. Number three is which would be feasible. Theoretically, you can come up with any brilliant design, but which would be more practical or feasible device structure from all the different options I have showed in this lecture. So this is, in terms of design, this is not the comprehensive list. I'm just showing you the major fundamental variations of graphene and carbon nanotube based transistor design preparation, but there are numerous other research people are talking about carbon nanotube based tunneling FET and other things. Okay, so that's all for this lecture. So now, yeah, so all three parts are done. Now let's talk about your paper. How many of you sent your template or draft? I think you sent, I think, yeah.
I only sent the abstract.
I told you to send you the basic structure, what are the major section or what are the things you want to focus on. So,
Then I can resolve that.
yeah, yeah.
I have exam, so can I?
Well, when you are taking more than one class, yes, you will have exam, but you have to finish.
Sorry.
Yeah.
I'll send it like around 7.
Okay, yeah, yeah. So yeah, send it to me by tomorrow, at least a draft plan of your paper. So because next week we will not have, we will see you again this Thursday, but next week we will not have any class because I am going to give you some hard deadline for some of the tasks related to your paper. Okay? And then from 3rd week of April, we will start individual presentation. That will be at least 15 to 20 minutes presentation of your total paper. So please send me the draft template of your paper before Thursday class.
This
Okay?
Thursday we don't have any class.
This Thursday we meet in the class.
We have class.
Yeah.